So, we started with the goal that we want to really achieve or solve every problem in the world. Of course, I mean this is an admirable goal, it is a lofty goal, as we discussed that AI researchers like lofty goals. So, that is one of their goals. And so, we wanted to formalize some representation for pretty much every problem in the world, right. And of course, we will not get there, but we will get to a representation that solves many problems in the world, of course, right, or that represents many problems in the world. In the context of that, we started out by talking about what is a state, because we will have a state centric view. In all of AI, you would find that state would be central. What goes into the state will become quite important. After the class, somebody came in and asked, how does human always figure out the state? And my answer to the student was that for now, for the purpose of our AI class, a human is always going to figure out the state. Now, if you are given some data and if you run some kind of a clustering mechanism later in some advanced level courses, you might get to a place where you can later claim that one cluster is one state, and then I am going to do all my downstream AI algorithms on the state space that I automatically figured out from clustering over this data. It is possible, I have seen this done, but it is relatively rare. Okay. So, for most parts we would assume that a human who has the problem in mind, the domain designer, we can use the word domain designer for this, the domain designer designs the state space for us and the AI folks are just interested in solving. Okay. Then we discussed that how do I represent a state, right, in the world, in the AI's world, in the AI's brain, how do I give the state space to the AI agent. And we discussed that there are many different ways of doing this. One is atomic, where each state is the most indivisible unit in my space, and let us say state is a number, and so you can't really understand what is happening internally inside the state. You just say that each state, each specific configuration of physical objects or my problems setting is a number, right, a unique number. And then we also briefly talked about propositional and relational, and we gave the example of the vacuum world. So, this is where we were in the last class. And the next thing that remains to be done is that we need to define a representation that the domain designer would give an AI agent and say, look, this is my problem, please solve it for me. Okay. So, of course, what the domain designer is going to say is that I have a set of states, but the interesting thing is that this set of states may be there in domain designer's mind, but he or she is not going to enumerate all the states for me. Okay. And this is going to be the fundamental difference between a lot of AI problems and a lot of other sort of graph theory problems, and we will come back to that. So, let us say this domain designer writes a code for me where he says, look, I will give you a black box. I will give you 2 black boxes or 3 black boxes, right. What are these black boxes? So, the first black box is that if you ask me, if you ask me whether you are in a goal state, then I will give you yes or no. This is my black box 1, and we are going to call it the goal test. Okay. So, notice that we are saying goal test. So, if you say I have reached this state, is it a goal? Is it a goal? So, the domain designed black box is going to say yes or no. Okay. That is one component of the problem that the domain designer is going to give me. The second component is that if you are at a state and you tell me that I am at this state, tell me where all I can reach from this state in one step, then I as a domain designer will tell you, okay, from this state S1 you can reach S5 by taking action or operator 3 and S9 by taking operator 5 and so on and so forth. So, at the internally what is going on is that there is a set of states, there is a set of actions or operators, and then if I am at a certain state, if I take an action, I get to a new state. This is my graph structure internally, if you think about it. Fair enough? and I will be at a starting state and I want to reach a goal state. Okay. And my starting state will be unique more often than not, there will be one starting state that I am in. My goal state, there can be many goal states, right. So, if my goal state is that Vishwajit should be sitting on this chair, then where Ansh is sitting does not matter. So, there may be many goal states where Vishwajit is sitting on this chair, but Ansh can be sitting on any chair. And in that way, I may have many goal states. So, you can't use the word the goal state, we have to use the word a goal state. This is very important. When you write, when you read AI papers, if they have been careful, they would not say the goal, unless there was exactly one goal in their problem. They will say a goal, because there can be many goals, and this is what AI folks sort of think from the perspective. So, again, so internally in domain designer's mind, the domain designer has a graph. There are states in the graph. Think of each state as a node. Intuitively, all their differences, graph nodes, and then there will be edges. Think of them as operators, actions that I can apply in a given state. Think of it as a directed graph. If I apply an action in a particular state, I get to the next state. There is that graph, but this graph is possibly so huge that nobody is going to write it out for you, and that is very important. This is actually fundamental in AI, because the problems are at least NP hard, as we discussed last time. So, more often than not, the problems that we will be dealing with will be very challenging in many ways, and one of the ways in which they can be challenging is I can't even write the whole problem in as a data structure. So, I will write it as a code, some kind of a black box, where I will give the AI person 3 black boxes. One is an expand function. This expand function says, if you are in a state, I will tell you what are the next states you can visit in one step. One would be the goal test. If you give me a state, I can tell you whether you are at goal or not. And last but not the least, I will tell you what initial state you need to start planning from. Now, with these 3 functions, I have defined an atomic agent for me, and the input would be exactly what I said, these 3 particular functions, and what the AI system is expected to achieve is a path from the start state to a state satisfying the goal test, right. And if my actions have costs, I may be interested in the cheapest path. If my actions do not have costs, I may be interested in the shortest path, right. Everybody with me on this? Now, I started with the lofty goal that I will define a problem where I will define a representation where all problems in the world can be modeled. Does it model all problems? Let us just quickly ask that question. Would it model all kinds of problems in the world? Okay, you guys seem a little lost. So, the answer is no, right, and the reason it does not model all problems in the world is A, there is no notion of uncertainty in this representation. If I take an action in a state, I always reach the one deterministic state, which is what the current formulation has, right. We will relax that, So, we will reach a different kind of an agent where stochastic actions could happen in the future, right? Or actions could have stochastic effects basically. And alternatively, this is a single agent view of the world. I am one agent, I am taking one action at a time, and that is the only thing that is changing the world. It is possible that there is an adversary that I am playing against. I am playing one move, the adversary is making the other move, and my goal is to defeat the adversary's move is to defeat me. Now, that kind of a setting is not naturally modeled in this representation, but we will study that too. Okay. So, in some ways we started with a goal of modeling every problem in the world, but what we have modeled more or less is a deterministic single agent problem where the agent is the only one making the change to the environment. Because if the environment automatically changes, then I will have stochastic effects obviously, right. Does it make sense? If it does not, this will over time make more and more sense as we go on in the course, all right. But in spite of this, the claim is that at least for this subset of problems, this will be able to formulate a lot of problems in the world, okay, a lot of problems. So, let us look at some such examples. So, one such example is the 8 puzzle problem. Everybody knows the 8 puzzle problem. I have 8 tiles in a 3 cross 3 grid. I am supposed to move these tiles such that I start from any given start state and I finally reach this particular goal configuration where all of them are numbered 1, 2, 3, 4, 5, 6, 7, 8. Many of you may have played 16 or 25 puzzle when you were kids. Right. Now, a question for you, can I formulate it as a search problem? Now, when we use the word formulate it or model it, you should not think about how to solve it. And this is the fundamental AI way of thinking. There is modeling and then there is algorithm. Remember we discussed. So, we are now talking about modeling. Modeling means, can I represent it into a set of states, set of actions, a goal test and a start state such that I will be able to give the inputs that my atomic agent needs, and the atomic agent may have some algorithms which are general algorithms and may be able to apply those general algorithms. So, when we think of modeling a problem as an AI problem, we do not think about what solution we will use, we think about modeling it as in one of the many ways to model a problem. And then for that particular formulation, there are already some algorithms that have been discussed and those algorithms can be applied. Okay. So, now here is a question for you. How would you formulate an 8 puzzle problem as a search problem, atomic agent search problem? What would be the set of states? You will have to be louder, I can't hear you. Each possible configuration of the board. What is your name? Ansh. Okay. So, Ansh says each possible configuration of the puzzle would be my state, right, the locations of exact all these tiles like 7 2 4, 5 gap 6, 8 3 1 is a state. What would be my actions? Yes, somebody at the back. Yes, what is your name? Abhyuday. Yes, Abhyuday. Shifting one of the tiles. How many actions at most might I have? 4. How many actions at the least might I have? 2, right? And instead of shifting the tile, let us say we are going to shift the gap. It will be easier to understand it, right. So, we will say that I will move gap right, I will move gap left, I will move gap to the top, I will move gap to the bottom. Right. What will be my goal test? Somebody on this side. What will be my goal test? It is not very hard, yes? The final configuration that we have, right. How many goal states do I have? Only one goal state. So, this is a problem where we can say the goal, right. And is there a notion of a path cost? Are there action costs? So, what can we say is the path cost? The number of steps. Okay. So, what we have done in this process is that we have converted our problem of going from any starting configuration to the final test, goal test. As a search problem, we have defined a set of states, we have defined a set of actions. If you start thinking about how many possible states do we have, even for this small problem, what would you say? How many possible states do we have? Nine factorial, right? We will have 9 factorial states because we have 9 tiles which can be arranged in, we have to arrange them in a specific sequence. Gap can be thought of as a tile if you want. So, for 3 cross 3 9 factorial, maybe we can enumerate the whole state space, but for 4 cross 4 16 factorial and then for 5 cross 5 25 factorial, we will not be able to enumerate, definitely for 25 puzzle, we will not be able to enumerate the whole state space. We will not be able to give you a graph, where you can run your Dijkstra's algorithm on it. So, always remember, you have studied the shortest path problem. This is no different from the shortest path problem the way we have defined it. However, the fundamental difference between the shortest path problems that you have studied and what we are going to study in AI is that my graph would be too big that I will never be able to store in memory. So, therefore, I will give you the graph in some implicit form. The implicit form here is that I am giving you a successor function or an expand function basically, and I am giving you a goal test, and I am giving you the start state. This is my way to let you build the graph if you want to build the graph. But of course, if you build the full graph, your memory it will go out of memory and you will never be able to solve the problem. Okay? So, this is what we will keep in mind as we study the next few weeks of lectures, that the problems are not really hard, we understand them, Dijkstra's, Bellman-Ford, whatever, we have our favorite algorithms for shortest path, but I can't even give you the graph. So, if I can't give you the graph, intuitively what might you do? What will you do? I have given you a state space, a starting state. So, I have given you this 7245 gap 6831 configuration. I have given you an expand function. What could you do? Who said randomly take? Yes, what's your name? Vishwajit. Yes, of course. So, Vishwajit says randomly take actions. So, just do a random walk in the space. Do not think about where you came from, where you want to go, just keep searching randomly, right. That is one alternative. There is nothing wrong with it per se, and we will come back to that particular alternative when we get to the local search class. But for now, there are different alternatives that we are interested in studying. So, what could be another alternative? Yes, what is your name?
Give each state space a score or something like that.
Give each state space a score, and then what do you do with the score?
We give the score such that as we move closer towards the goal.
But how do we move closer is the question. See, I am asking a more fundamental question. I am only giving you the start state. So, what do I do next? Yes. We move to the neighboring states. What is your name? Chinmay. Chinmay says let us move to the neighboring state. But which neighboring state do we move to? Do we have to move, or can we just do the thinking? See, look, we are building an AI system. The AI system is like thinking. We do not have to play. We do not have to play right now. We are just thinking in our mind. What should be the best action to do? So, it is not like we have to take this move in the real physical environment. It is like we can do the planning in our brain and then decide what to do. We are allowed that. So, we are in the thinking phase, not the acting phase. Yes. What is your name? Suruchi. Yes. Sukriti. Yes.
Possibly we can develop like a heuristic or something that, like, for example, for a puzzle we know that getting the center piece in is first is the right way.
Very good. So, you are all running slightly ahead of me, but that is good. So, Kriti says let us define some heuristic, and that heuristic tells me what is a good state, and we will come back to that towards the end of this class or this lecture slides. So, we are currently in the world that we have defined. So, our world is that there are a set of states, a set of operators, a start state and a goal test. I am not giving you anything else. So, notice I am not giving you anything else. This is my current version, and that is why, because I do not have any idea of which is a better state, which is a worse state, these problems are called uninformed search problems. We are in an uninformed search problem. We have no other information, and so therefore, we have to do whatever we have right now. We have to do the best we can with the information that has been provided to us. I am asking you a more simpler question, by the way. I am at a start state. What could I do? What would be the first step I will have to do? Find the moves. What is your name? Akshay. Okay, find physical moves, right? Akshay says find physical moves. How do I do that? My domain designer has given me something. What has the domain designer given me? The expand function. So, I give my domain designer the starting state and say, please expand. And when the domain designer expands, or the black box expands, what do I get? A set of states which I could reach in one step. For example, in this configuration 7245 gap 6831, if I move gap to top, I should get 7 gap 4, 5 to 6, 831. And if you keep doing this, this leads us to a search space. Okay. This is should be fairly intuitive to you. This was my starting state and I took the move gap to the top action, then I got to this state, and this I can do with the expand function. I got to right, I got to this state, and so I now got 4 new states. Now I can technically recursively apply the expand function and keep expanding my search space. Now notice that this is different from Dijkstra's algorithm. Well, not exactly, but at least we are only looking at those states which we could reach from the start state. So, we are not even interested in states we may not ever be able to reach from start state, or those which are very far away from start state which we do not need to reach to the goal. So, therefore, we will end up expanding more often than not far fewer states than if I was giving you the full graph. So, that is the first intuition that you have to look at. Yes, Sukriti. No, we are getting exactly there. So, the question was, is it any different from depth first search? No, this is the algorithm I want you to come up with. It is not surprising in hindsight. You will say, oh, I thought AI was cool, it is just depth first search. Well, it will get cooler slowly. But look, we have modeled things in a certain way. Why have we modeled in a certain way? So that we can be general. Now, we pay the cost of generality, we basically expand this state space graph and we call it the search tree. By the way, it is a search tree or a search graph? And this is a good question. So, can states be repeated? For example, if I move the gap up and then move the gap down, will I get the same state? Yes. And now the question for you is, what do I do about the repeated states? And I will come back to it, but you keep thinking about it at the back of your mind. So, we can have a search tree or we can have a search graph, but to reach to the search graph we have to do what is called the duplicate detection, of course, because we are only giving it to the expand function. The expand function is giving us new states. We have to somehow say, have I seen this state or have I not seen this state? And if I have to do full duplicate detection, it is possible that it will take a lot of memory anyway. So, therefore, in AI, at least for now, we are going to study the search tree version of it. In the search tree version, any search state could, 2 search states could represent the same world state, right. This graph does not show it, but if I do a gap down action here, I will get to the same starting state, and for now we will allow it for now. Okay. So, our goal is to make sure that this is a general enough representation. So, let us take another kind of problem. This is a robotic assembly problem. I want to complete the assembly, like think about an IKEA store or a store where you get all these parts and you have to assemble the table or a desk at home. You know, in India we do not have to do it, we have people to do it, but in western countries I have assembled my own table and my own TV and so on and so forth. No, not the TV in terms of opening up the TV, but putting it on the stand and all of that. So, what happens? They give you an assembly parts and they give you the screws and everything, the tools, and they give you the step by step instructions of how do you assemble, right. So, suppose this was a problem where I gave you all the tools, and what will be my state? My state would be the particular pieces and how I have built my particular part, and my actions would be add another part, or it could be lower level where robots will move their joints, and based on that the particular piece will go into the right place, and my goal test is to check whether I have gotten the assembly completed and correctly, right. Or any kind of a shortest path problem, like going from one city to another city. The book uses the example of going from Arad to Bucharest in Romania, and there you can always think of it as a search problem where your starting state is that you are in Arad, all the states are various cities, actions are drive between cities, goal is to be in Bucharest, and you have to find a solution, a sequence of cities such that your total time is minimized, your total driving distance is minimized. Now, these are easier ones, but here is another fun one, okay, a slightly unusual one. So, let us say I give you the n queens problem. Do you know the n queens problem? The n queens problem is that you have to place n queens on the chessboard, n cross n chessboard, such that the n queens, no two queens should be attacking each other, and you know that queens attack each other horizontally, vertically and diagonally. Is this a solution to the 4 queens problem? Yes? Neither these 3 attack, nor these 3 attack, nor these 3 attack, and so on. So, nobody attacks anybody. So, they are happy living in the same chessboard. Right. Now, if I had to solve this problem, can I still formulate it as an atomic agent search problem? What will be my set of states? What will be my set of actions? We will place queens one by one. What's your name? Parth. So, Parth says we will place queens one by one. So, my starting state would be empty board. My starting state would be empty board. My set of states would be not number of queens. If you say number of queens on the board, then you only have up to 4 states. That is not enough. But what would it be? It will be a partial configuration of the board, right? And you can be clever, you can say first I will place the queen in the first column, next I will place the queen in the second column. It does not matter, because order does not matter. It does not matter whether I place queen 1 first or queen 3 later, and queen 3 first or queen 1 later, it does not matter. So, we can become smarter in defining our search space. But my operator would be adding one more queen, start state would be empty board, and the goal test would be all queens placed and no two queens attacking each other. Very good. So, now you can start to think that, oh, we can model many problems in the search representation, and the book has many more, right. So, you should check the book for more examples of this. You should even try it yourself. So, one of the skills that you should have at the end of the AI courses, if I give you a new problem, you should be able to model it in one of the various problem representations of formulations we study, and for now you should focus on the basic search formulation, the atomic agent search formulation. Now, when we implement it, there is a world state and then there is a search node, and those are 2 different things. So, a state is the representation of the physical configuration. A node, however, is a data structure that has the state, but also has the parent information, what actions are applicable, what is the cost up to this point, what depth am I in the search tree, etc., etc. So, actually when you start implementing things, a search node will have many more things that you need to keep track of, but that is okay, right. We are not worrying about it for now.